Okay. So one more factor, like a match number, that tells us like how an object speed is compared to the speed of sound. So we know the speed of sound. From there we can imagine what is the speed of other objects, right? So here the for the these supersonic travels, like these ones, the supersonic one, its match number is 1. So this type of supersonic can travel the same speed as sound. And then the transonics, it's about the same speed as the, oh, I think I made a mistake. So supersonics, they travel little less speed than the sound, so they have a less speed than sound, so that's why the Mach number is less than 1. Then the transonic, they are about the same speed as the sound. Then when we go to supersonic, they have higher speed than the sound, that's why the Mach number is larger than 1. And then hypersonics, they go beyond the the speed of sound, so they go 5 times higher than the speed of sound, so their Mach numbers are getting larger. So if you're curious, like to know what is the fastest traveling jet on the that we have now, that's X-15. That's North American X-15 aircraft. So its recorded speed is 7,200 kilometers per hour. That's Mach number is 6.7. That means it is about 6.7 times higher than the speed of sound. All right. So again, what is the speed of sound? Can you remember that? Okay, so escape velocity of rockets. So rockets are traveling really fast, right? So we have like rockets carry a huge amount of energy, or the fuel. Sorry, give me a second. I'm sorry, you know, kids are at home, they're doing homeschooling, so they need something else, so they're coming to my room. Sorry about that. All right, so the back to the topic. So the rockets, so the escape speed, you know, like if you throw something here, like if I throw this ball, it's not going to go to the space, right? So it will be falling down. It will be showing a projectile, like a curvy path, and it will drop onto the ground. But if you can throw this object with a high speed, you can make it go around the earth. And if you want to go beyond that, like you want to throw this ball into the space, let's say, then you need to make this much of speed. So if you can throw this ball with 70,700 miles per hour, then this object will escape from the Earth gravitational field. So it will go into the space, right? So can we make that go fast? You may try. So you don't need fuel. You may throw it with that speed, and that way you can throw the objects into the speed. To the space. So the speed is 7.9 kilometers per second. In our regular units, it's miles per hour, right? So it is 17,700 miles per hour. Here, the Mach number is 20. So it's 20 times faster than the speed of sound. Then, you know, like we feel we are very steady here. I'm not moving. I'm just sitting still and I'm not moving. But it's not the truth. We are moving, right? So if you think about the earth, so we are standing up on the earth. We are standing on the earth, and earth is orbiting around its own axis. The speed is 460 meters per second. So it's about 1,000 miles per hour. Can you imagine? Like we are spinning ourselves, right? Because we are standing up on the earth, and earth spinning 17,000 miles per hour. So I cannot demonstrate it. It's really quite a speed, right? The 1,000 miles per hour. You can imagine the comparatively by, like when you're driving your car 100 miles per hour, maybe once in a while you make your car go 100 miles per hour, right? So you may compare with that. It is a quiet speed. So we are moving. So even though we think like we are in a stable world, we are really not. We are spinning. Not only that, we are also going around the sun, right? So we are going orbiting around the sun as well. We call this as revolving. So we are revolving around the sun, and that speed is 67,000 miles per hour. Can you imagine how fast we are? So we are not only moving in a circle, also we are spin around us, and also we go around sun, right? So that is quite a big speed here. So it's not 10 miles per hour, it's 1,000 miles per hour, and also 67,000 miles per hour. So you may compare the speeds comparatively with the sound waves. All right, so the speed of, remember, like we learn about two types of waves. One is a transverse wave and the other one is longitudinal wave. So the other day, one of you asked a question about the ocean waves. So as I mentioned, ocean waves, the water waves, they can find in both as transverse waves and longitudinal waves. So transverse waves mean the wave propagation is perpendicular to the particle movement. So if you are on a shallow water and the water is like moving up and down, but you will see there will be a wave propagation toward the shore, right? So that is a transverse wave. So normally if you think about a slinky, the slinky is moving up and down, but the wave is propagating in the horizontal direction. So those are transverse wave, and the longitudinal waves are different, like tsunami waves, or like when you're playing in the beaches, you know, like we get the water waves that's coming to us. So that way it's the particles are moving with the wave in the same direction. So those are longitudinal waves. So we can calculate these wave speeds. So they're creating in a different way, right? So they have two different equations to calculate the speed of waves. So for the transverse wave, we use this equation, V equals square root of T over mu. I know these symbols confusing. So let's see what are these. So basically V stands for wave velocity. T is the tension on the rope. Tension means the force that acts on the rope. If you're making a wave on a rope, if you're making the wave on the water, then there will be force on the water. So the tension on the rope in this one. And mu means the mass per unit length. So if you measure the mass for a 1 meter length, then that is the density of the mass, right? So mu means the mass per unit length. Then for the speed of longitudinal waves, you know, like they're creating by the pressing and compressing and stretching, compress and stretch. So in this case, the velocity can be calculated using this equation. So P means the pressure of the atmosphere, D means the density of the material. So you are talking about sound waves, right? So to create the sound wave, there should be air column. So we need the pressure of the atmosphere, the air atmosphere, and the density of the air that you are talking to. Now, in this case, if you look at this one, here the P is the pressure of the atmosphere and the D is the density. So let's say I'm sending a sound wave through through air, and also let's say I'm sending the same sound wave through a metal. So, you know, like in metal, the density is high, right? So density is high in metal. So D value going to be higher than it's in the air. So when you have a higher number, this whole thing, like when you're dividing a number by a big number, the value will be small, right? So the speed of sound is depend on the density of the material. Now, without using any of this equation, we can use this equation on the bottom over here, the V equal F over F times lambda. That means the velocity of the wave, it doesn't matter whether it is a transverse wave or a longitudinal wave, we can use this equation. So V is the wave velocity, F means the frequency, and lambda is the wavelength. So by now you know what is a frequency, and yeah, I believe you know what is a wavelength is as well. So we can use this equation no matter whether it is a transverse or longitudinal. Okay, so in the homework or exams, you need to figure it out, like what are these equations are using for. I will give you a couple of questions on the next homework to practice this equation. I will give you the value for tension and the value for mu, and I will ask you to calculate the velocity. I'm not going beyond that. But if you're planning to take any other physics classes, you will use this equation a little bit in detail. All right, so let's try calculating a wavelength of some sound waves. So as you remember, the speed of sound is 340 meters per second. All right, so we can use that last equation I mentioned, like V equal F lambda. Then we can calculate the lambda. So we can rearrange this equation to be lambda equal V over F. So if the frequency is 20 hertz, the speed of sound is 340. So you can take 340 divided by 20. That will be 17 meters, right? Right? So the lambda is 17 meters. Now remember the unit. So lambda is a wavelength. It is a length. So the units will be any unit that measure the lengths, right? So if you are using SI unit, the metric units, that will be meters. If you're using this just US custodial units, then that will be miles, right? But if you go to any European country, then the units to measure distance will be kilometers, right? Their distances and the speeds are marked in the roads like kilometers per hour. Here in US, we have miles per hour. Why is that? We don't like to do what Europeans are doing? Not really. It's because we have long distance, right? So the country is comparatively larger than European countries. So when we are traveling from East Coast to the West Coast, we have a thousand of kilometers to travel, right? So if we go kilometers per hour, our numbers are really large, and it is not usable. It's not user friendly. So that's why we go for miles per hour. So the numbers are smaller and it's usable. It's user friendly, let's say. All right, so for a frequency of 20,000 hertz, we again can use this equation. So lambda is equal to V over F. Velocity is 340 meters per second, and frequency is 20,000 hertz. So all the values are given. Only thing is you have to calculate the unknown factor, the lambda, right? So it will be 0.02 meters. It's about 1 inch. So you see, like when you're changing the frequency of the sound wave, the wavelengths are changing. Now, if you're familiar with any musical instrument, so you're changing the frequency, right? So the 7 notes, that comes with different frequencies. So depending on the frequency, you're changing the, let's say you're playing a flute. So you're changing the length of the air column that you're vibrating. So that depends on the frequency. So when you're changing the frequency, remember, like sound is traveling with the same speed. So the sound wave speed is 340 meters per second, but by changing the air column that you are vibrating in the flute, you can get different frequencies. So when you have different frequencies, you hear different sounds, right? Similarly, in any string equipment like instrument, like guitar, so you're changing the length of the string, right? So by changing the length of the string or the thickness of the string, you're changing the frequency. So when you have different frequencies, you hear different sounds. So if you are a musical person, like who likes to play instruments, even though you don't know the science behind it, you're practicing changing these wavelengths. All right, so let's move on to the little bit advanced topic in waves, like electromagnetic waves. So by now we talked about these waves like sound waves. So mainly we interested in sound waves in that one. Also we talked about the 2 types of waves, transverse wave and longitudinal wave. So we can make the transverse waves using any string or a slinky, something like that, right? So let's see what are these electromagnetic waves, because we are using electromagnetic waves everyday life. Phone, we are using electromagnetic waves. All right, so on the chat, I receive a question. Yes, go ahead, Daya. Sorry if I pronounce your name incorrectly.
It's there, but I had a question. So the last ones, to make sure, so I understand how you got the meters, but how did you get the feet part?
Oh, this one. Oh, you can convert the units easily.
Oh, you just converting the 17 meters into feet, correct?
Yes. Okay. So you can even Google like how to convert meters into feet. 1 meter, 1 foot mean 12 inches.
Okay, I'm just making sure that I'm
yeah. I will not ask you to convert units because I didn't talk about it. But when we move on to motions, we will talk about units. Okay. Now, in the questions, like if I give you this equation, like speed is 340 meters per second, frequency is always hertz, right? If you use hertz, then you end up getting meters because your speed is in meters per second. And the frequency hertz means per second, so units will be meters. Here, I just put it in feet because you're familiar with that unit rather than meters, right? When we say 1 meter, we don't feel it. But when we say 1 foot, we feel it, right? Because we know, like, how much is it? It's about the length of your foot, right? And inches, you know, like 1 foot is 1 foot is 12 inches. So from these numbers, you get a little sense, like physical sense, than having meters. So that's why I have it there.
Okay.
Yeah, thanks. So you can always stop me and ask questions. It will slow down us, it's okay. Because we are not in a race to catch every concept in physics. All right, so let's move on. Electromagnetic waves. So now read the word, it's electro and magnetic, right? So there should be electric part in there and also a magnetic part in there. So electromagnetic waves are transverse waves. So the type of this wave is transverse. So it's a combination of oscillating electric field and a magnetic field. I know it is hard to visualize, but you can imagine like this. So as you see in this picture, these blue color arrows represent the electric field, and the this red, I don't know what color you're seeing from there. I draw it in red color. So maybe sometimes you see it as a brown color arrows. So these represent the magnetic field. So you have this electric field and the magnetic field, they are vibrating or oscillating in perpendicular to each other. So let me grab 2 pieces of papers, let's say. All right, so here I have 2 different colors papers. I don't know, you can see me. You can pin my video so you can see the what I'm doing here in front of the screen. So here I have a green color one in the bottom, and this is the gray color one. So they are perpendicular to each other, right? So let's say this represents the electric field. So electric field vibrates up and down. Then the magnetic field vibrates horizontally, left, right, left, right. This one up and down, left, right. So likewise, it oscillates, and at the same time, it's travel horizontally. So up and down on this one horizontally. Okay? So it's traveled along in the horizontal direction. So here, as in this picture, electric field vibrates up and down, and the magnetic field vibrates in the horizontal direction, like perpendicular to that plane. And the wave travels to the right, this way. So they are perpendicular to each other. The electric field, magnetic field, and the direction of motion, the speed of the wave, are perpendicular to each other. Right? Then now there's a wave, so there should be a speed, right? So the speed is in the horizontal direction in this one, and the wavelength will be whatever the distance from trough to trough, or valley to valley. So here, from the top point here to top point there, that is the wavelength of the wave. Now you can measure the distance from the trough at the magnetic field and the trough at the magnetic field over here. So that is the wavelength. So they are equal. So the wavelength will stay the same. It doesn't matter which point to which point you are measuring, except you need to measure the distance from likely points to another likely point. All right. So the speed is, we call this as the speed of light. So the electromagnetic waves are traveling with the speed of light here. Okay, so this is a better picture of that. So you see, like, red color lines represent the electric field vibration, and the blue color one represent the magnetic field vibration. So if you are learning this 3-dimensional factor for the first time, you always need to get 2 planes and visualize it. So you have something like this. So this plane is perpendicular to this one. And is there any other plane that perpendicular to these 2? Yes. So if you use your hand and if you keep your 3 fingers like perpendicular to each other, so those are the 3 dimensions, X, Y, and C. X, Y, and C. So if you go X and Y, that is just a 2-dimensional. This is just 2-dimensional. But if you go to the other direction, like perpendicular to this one, that is the 3rd dimension. So that is, we call this as a 3-dimensional picture. So this is a 3-dimensional picture. That one perpendicular to the blue color ones. Red and blue are perpendicular. So the magnetic field vibration is perpendicular to the electric field. All right. So electromagnetic waves transport energy through empty space. Now remember, like for sound waves, we need air to vibrate. For other waves in springs or the any slinky, we need that material to take the energy. Like water waves, the ocean waves, it need water to make that energy transfer. Now for very interestingly, electromagnetic waves does not need a medium. So they are traveling in the space. So light wave is an example of electromagnetic wave. Now there are a whole bunch of electromagnetic waves. So we call this as the electromagnetic spectrum. So in the electromagnetic spectrum, I will move on to the next slide and I'll come back to the previous one because this picture is much better that we can compare the sizes with the real objects. So in the electromagnetic spectrum, we have radio waves. Now over here, I listed down the wavelength in meters. So 10 to the power 3, that's 1,000 meters, right? So 1,000 meter, that means 1 kilometer. So if the wavelength is 1,000 meters or 1 kilometer or larger than that, those are radio waves. So here, the size of the wavelength is longer than a height of a building, a huge building, tall buildings, okay? So those are the radio waves. So radio waves have a larger wavelength. Then comes the microwave, that is 10 to the power minus 2, that's 0.01 meters. It is small, right? So those are microwaves. So after the radio waves, we have microwaves, which it is large wavelength, but not large as radio waves. Then comes the infrared. So when you go to the microwaves, it's about the size of a person and an ant. So some wavelength size is about in the range of these sizes. And then come the infrared. So that's about a pinpoint size. It's 10 to the power minus 5 wavelength in meters. And then come the visible region. So visible region, the wavelength is in the range from 300 nanometers to 700 nanometers. It is about the size of a bacteria. So that is the only region that humans can see. So we are observing only this region, the visible region of the electromagnetic spectrum. Then come the ultraviolet waves. So those are the size of a molecule and we can't see those. We cannot even see infrared or microwave or radio. We can't see any of these waves except the visible region. So we are seeing only a short range of this electromagnetic spectrum. Now ultraviolet, then after that X-rays. So X-rays, the wavelength is about 10 to the power minus 10 meters. Okay, so that's the size of an atom. Then comes the gamma rays, that's 10 to the power minus 12. You see like the wavelength is getting shorter, right? So that's the smallest wavelength. So we have gamma rays. Like if you see anything below 10 to the power minus 12 meters, that's a gamma ray, and that's an atomic nuclei size. Okay? So now, if you look at the frequency, it's behave in the opposite way. So the frequency for gamma rays are the largest, 10 to the power 20 hertz. Look at the frequency. That's why it's carry a high energy. So it has a high frequency. Now, if you go to the radio waves, it's 10 to the power 4. So it frequency is the smallest is for the radio waves, and their energy is really, really comparatively minor compared to the gamma rays. Now, gamma rays can kill us, but radio waves can't because it does not have that much energy. Okay, let's go back to the above slide. So here, the electromagnetic waves propagates with an incredibly large velocity. So we call this as the speed of light, and it's represented by a letter C. So that is a constant value. It's 300,000 kilometers per second. Okay. I'm not going to try reading this number, but if you are good at reading numbers, you may try this. That's miles per hour. Okay, so let's read it. I don't know. I should practice that. You may try reading this one. All right. So that's how many miles per hour. So that look at the speed. So in 1 hour, this electromagnetic waves, any electromagnetic wave can travel in this speed. So light can travel in this speed. Microwaves can travel in this speed. Then the radio waves will travel in this speed. Gamma rays, the same speed. right? So that's the speed. Then, you know, the frequencies are different and the wavelengths are different. So they're behaving differently. Now, here, as I mentioned, this is the visible range. So look at this. So we think that we know everything. Science is incredible. We can see everything, but no, we can't see unless we use equipment, right? So here, this is the normal human visible range. So we're seeing only this short range. So we don't need to be proud about it, right? But if you go for other animals like snakes, they can see the infrareds. So the snakes can see the infrared region. So some animals see some other waves as well. So it depends on each creature. So each creature has different range of visualization. So here, the humans can see only this visible spectrum that's go from indigo to red here. So it's go from about 350 nanometers to 700 something. So, you know, like we call this blue red, but, you know, even in the blue, we have a high range, right? So we have light blue, dark blue, sky blue, right? So we have a different range in there, but normally any color, like in this wavelength range, we should be able to see. All right. So when we go in the wavelength curve, when we go to the radio wave side from the gamma rays, we see that it's increasing wavelength and it's decreasing the frequency. That decreases the energy as well. So wavelength and the frequencies acts different in the opposite way, but the frequency is related with the energy. So when we have high frequency, that means it has higher energy. Then when we have low frequency, that means it have low energy, but it will have high wavelength. So they acts opposite. All right, so short wavelength, that's UV and X-rays and gamma rays. So lambda, the wavelength is less than 400 nanometers. Is it true? So if you look at the visible range here, I think this is a good one. So you have visible range here. So it's 400 as the listed it down here like a wavelength. So if you have something less than that, we go for UV ray, X-ray, or the gamma rays, right? So that's the range that we're going for, shorter wavelengths. So here, shorter wavelength, which are UV, X-rays, and gamma rays. Hold on, I think I miss you up. All right, hold on. So here, these are the short wavelengths. No, I was good. UV, X-rays, and gamma rays are the shorter wavelengths. Yeah, I was right. So sorry if I make you confused. So UVs, X-rays, and gamma rays have shorter wavelength than our visible light, than blue, let's say. So lambda is less than 400 nanometer. That is 400 nanometer down to say 0.01 nanometer and less. So ultraviolet light, X-rays, gamma ray sources. So these are the just pictures to show you like what are the ultraviolet light, X-ray tube, and a gamma ray source. So if you're going into the medical field, you will be taking some X-rays. Actually, even now when you go to the dental, you take X-rays, right? So we are using X-rays somehow in our body as well. So these wavelengths are electromagnetic waves. So when these waves enter into an atom, it can ionize the atom. You know what is ionization is, right? Remember, like in electricity, we learn about like we can electrons from atoms, and those electrons can be combined into another atom and make it positively charged, another one negatively charged. So we can do that by using these waves. So when we send these electromagnetic waves into an atom, it can knock out electrons and make the atoms ionize, and it will produce the radiation. So that's why when we are using X-ray machines, we don't stay in there. But these days in the dental, we are using very low energetical X-rays, so it's not harming that much, but still there's an effect. So that's why we are taking those X-rays once in a year, and also we are wearing that lead cover to protect our heart and other important organs that we have. So X-rays and gamma rays can be penetrate through matter. So when you send visible light through an object like a piece of paper, it blocks the light, right? So when you light up this paper with a flashlight, there will be a shadow and the light cannot pass through. But for X-rays, that can pass through our muscles. It cannot go through the bones, but it can go through the muscle. So that's why it's create images when we're taking X-ray pictures. All right, so these wavelengths travel at the speed of light. So I mentioned that value already. So this is 3 times 10 to the power 8 meters per second. So in miles per second, it's 186,000 miles per second. So the we use the symbol C to represent the speed of light. That number earlier was in miles per hour. So I had hard time reading it, but this is miles per second. So I'm making that number smaller. So note to the, if you're getting confused, look at the number, the unit. So this unit is different from what I have in the earlier slide. So in miles per second, the speed of light is 186,000. Okay. But in scientific books, we are using 3 times 10 to the power 8 meters per second. So this is the scientific notation. 10 to the power 8 means 1 and 0 eighths. So these speeds were predicted by Maxwell. So light propagates at a speed of about 3 times 10 to the power 8 meters per second. So, you know, like you can calculate the speed by taking the distance traveled in a particular time. So you take the travel distance divided by time. So from there, you can even calculate how long it traveled in a second. So when we say 100 miles per hour, that means we are traveling 100 miles in 1 hour. Likewise, here we have 3 times 10 to the power 8 meters per second. So that means the light travels 3 times 10 to the power 8 meters in a second. Or in miles, in a second, the light can travel 186,000 miles. So if you want to travel from Washington to Richmond, how many seconds it will take? Not even a second, right? Because we don't have 186,000 miles. All right, so that's why we can receive the phone calls right away, even though your friend lives in the other corner of the world. So that they're sending electromagnetic waves which can travel really, really fast. So you are getting that electromagnetic wave coming to your phone really quickly, less than a second. So you get it, the communication really fast. So regarding the light, so light can cover about 300,000 kilometers in a second. So that's incredible. So it can travel in long distances. So in 1 year, light travels a distance of this much kilometers. Yeah, so that is a very big number. So this number is very important for us. Think about it, like light is traveling in that much fast. So when we look at the sun, we see things, right? So that light might have produced like little while ago. It's not really producing the light right now. So that light takes some time to reach to us, right? So when we see that an object is in somewhere there, so it takes a little bit time there. So actually in astronomy, we are dealing with large distances. You know, like when we are measuring the distance from the sun to earth, it's 93 million miles, right? So 93 million miles, and light should travel that much distance to reach to us. So you may think about like how long it will take. So light travels 186,000 miles per hour, 186,000 miles per hour. Yeah, let me go back to the above slide so you have numbers invisible. So 186,000 miles per second. So that is the speed of light. Now from sun to the earth, it's 93 million miles. So you can think about like how long it will take to travel, right? So the light is traveling at quite a speed, but still it takes a little bit time to reach to us. So we measure the distances in light years in astronomy. So in light years, basically 9.46 10 to the power 12 kilometers is a 1 light year. So 1 light year, that means the distance that light travels within a year. So that is light years. So we are using light years to measure the distances. So for example, Proxima Centauri, that is the closest star to the sun. Sun is the closest stars to us. Proxima Centauri is the closest stars to the sun. So basically Proxima Centauri is the closest second star to us, right? So the first closest one is sun. The second closest one is Proxima Centauri. It's about 4 light years away from us. That means the light emitted from the star will take 4 years to get it to the earth. So when you're seeing the Proxima Centauri in the sky, we are seeing a 4 years older picture, not the current picture. So maybe that star is not there. It's gone 4 years ago after emitting the last light, piece of light, right? So that's incredible. So you're seeing stars in the sky. They are not real. You are not really seeing a current picture. You're seeing an old picture. Okay, so we are basically seeing an old picture of the universe, even though we think like we are active and we are seeing things correctly. We are not. We are seeing the old picture of things. All right, so this is another example. So COSA called SDSS. You know, we are out of naming things with the real name. So we are using numbers and letters. So this is a COSA. So it's been reported to be 12.7 billion light years away from us. So this estimated age of the universe is between 13 and 14 billion years. So we are calculating this age of the universe by comparing it with the speed of light. So that's why we say that time traveling is possible. So if you want to, with the current definition, we are defining our time according to the speed of light. So if we can travel faster than the speed of light, then we should be able to go to the future. If you go in the negative way, like negatively faster than the speed of light, then we can go to the past, right? So scientists keep trying in time traveling. So time traveling is not a myth, it's coming up. People are trying it, right? So the technique, what is the technique that we're going to exceed the speed of light? We still don't know, but it is something possible in sciences, right? So anyway, so if you can travel faster than speed of light, you can go to the future. Okay, so what time is it? Still have a couple of minutes. All right, so in physics, the Maxwell equations are really important. So Maxwell is a Scottish physicist, and he lives in between 1831 and 1879. So he's a great theoretical physicist, and Maxwell equations tells us kind of Lenz's law and the other law that we learn. But here Maxwell is the first one to come up with all this idea, and he's the one who first taken a color picture. So it's a color photography started from Maxwell. So basically Maxwell equations, the concepts he presented can be listed down as 4 steps like here. So the first one, electric field lines originated on positive charges and terminate on a negative charge. Remember, we learned about this, right? So the electric field is defined as the force per unit charge on a test charge, and the strength of the force is related to the electric constant, epsilon 0. So that's the permittivity of the space, right? So that's the first Maxwell's theory. So we already learn about it when we are learning about electricity. Then the second one is magnetic field lines that are continuous and having no beginning or end. Remember, like we talk about it starting from north and go to south. Then after that, what happened? It's go inside the magnet, right? So it's a loop. So there's no beginning or end to the magnetic field lines, and there are no magnetic monopoles. So we cannot isolate just a north pole and a south pole. So that's his second theory. And the third one, a changing magnetic field will induces an electromagnetic force. Remember, like when we are moving a magnet, it can induce a current in a circuit. And the fourth one is magnetic fields are generated by moving charges or by charging electric field. Sorry, changing electric fields. So remember, we learned about like what is the source of the magnetism? That's moving charges, right? So Maxwell equations comes from these 4 ideas. I'm not going to list down the Maxwell equations mathematically because it comes with integrations and other things. So I'm not going to mess you up, but you basically remember that there are 4 Maxwell equations that relate the electric field, magnetic field together and inducing a current. So you need to know like roughly what are the Maxwell equations are telling. This is the first photograph that's Maxwell developed in 1855. Okay, so that is a ribbon. It's like a butterfly, right? So it's a picture of a ribbon, a photo, like a real photo, a color photo. This is the first photography has taken in 1855. I don't know, when I was little, like 1985, 80s, this color photography is not that popular. These days we have our phones and we can take any color picture, right? But even in 1980, 85, we didn't have color photos. My baby pictures, I don't have color baby pictures. It was very rare. Only those people who are rich can take colorful pictures. Right, so it's 10:20. I will take your attendance and then let's do a couple of questions on TopHat. Then I will close the class, but you can stay here if you have any questions from homework, or if you are confused with something, if you need help understanding any theory, preparing for the exam, you may stay here, right? So let's take your attendance and do 2 questions on TopHat. Oh, by the way, in the beginning of the class, I share a video. Have you had a chance to watch that?
No.
Yeah, if I play it on my browser, I don't think you can see it clearly, but let me open it. Let's try. I know for some of you, it is not transforming the videos really nicely, but this one is a really interesting one. If you were in the class, I would try this one in the class, because I can switch on the sound in front of the class, and then you can clap. When you hear the sound, you can clap. So when it's propagating to all the way to the back of the classroom, those who stay in the back of the classroom are clapping later than those who are in the front. Can you see the video on the screen?
I see YouTube.
Okay, nice.
I see the video, yes.
Okay, so I'm going to play it now. Let's see. Yeah, if you can't see my screen, you can play the video that I send you, the link I send it on chat. That's a virtual way to see sound. Okay, so there's a device in front of the first person here, which is making 80 beats per minute. And you see, like, there are people in distances. So watch their arms, like how fast they are hearing. Like when they hear the sound, they clap. Okay. They are 20 meters apart. Okay, see that she claps, but they're still not. Now she claps likewise. So look at this. This is this real sound wave. If you watch the motion of the arms, it's really a wave, right? So that is the sound wave. Okay, he opens, she closes. Yeah, it's an interesting video. You may watch the video. We should have done it in the class, but if you have friends around, you may try it. So you may play a sound in front of the room, and then let's see like how your arms are clapping. Okay, so that's representation of the sound wave motion. And you notice like it takes a little bit time to travel to a distance, right? So when I speak, if you are in distance away from me, then the sound waves will take a little bit time to propagate. Now I can find my TopHat. Let me find it really quickly. Okay, send your attendance. Okay, I will keep it minimized. can you see it? I'm not sure whether I'm sharing it correctly.
Yes, we can see.
Okay, so after you send the attendance code, please try answering the question. Okay, so when you're answering, you have to visualize properly, like what are these directions represent. So this is in a one line, so they are not perpendicular, right? But this one, like it is perpendicular to both B and E. And so likewise, please read the alignment here. And you know, B represent the magnetic field, E represent the electric field, V represent the speed or the velocity. All right, so I believe almost all of you got it. So I'm going to close counting the attendance. Do I have anyone who need more time? Okay, for now I'll keep it for a second. Let's look at your responses. Okay, nice. So I have quite a lot have good correct answer. All right, so look at this. If you look at the answer C here, V and E are in the same line, but it is going into the page like this, right? So E and V are in the same line, but V is perpendicular to V and E. Remember the theory, the magnetic field, electric field, and the speed should be perpendicular to each other. So there should be in a, like in our hand, like 3 fingers perpendicular to each other. So here, V and E are not perpendicular to each other. So it is an incorrect answer. Then this one, B and E are in the same line, so they are not perpendicular to each other. So I have to keep B out of there as well. So this is not a possible way of producing electromagnetic wave. Now this one, E and B are perpendicular to each other, B and V are perpendicular to each other, and V and E are perpendicular to each other. So B, E perpendicular, so all 3 are perpendicular to each other. V is perpendicular to B, B is perpendicular to the E, and B is perpendicular to E. So all 3 are perpendicular to each other. Okay, I agree, it is a little bit hard to visualize because here you see this is 90 degree and that's 90 degree, right? So you will confuse, oh, they are perpendicular. I know V and E are perpendicular, V and B are perpendicular, but do we have B and E perpendicular? No, then it is not an option. Okay, so answer is A. I will stop counting your attendance and let's move on to second question. The last question for the day. Okay, so if the wavelength of an electromagnetic wave is about the radius of the earth, so radius of the earth, it should be larger than a building, right? So what type of radiation is it? Okay, so let's look at your responses. Maybe you missed that part, right? Let's see. Still, I have a big ratio having correct answer. So it is a radio wave. So you need to look at that graph, the picture where I had listed the electromagnetic waves. So those who say wavelength can't be that big, I expected like most of you will answer that way, but you didn't. You say visible light. Visible light wavelength cannot be that big. How comes? If it is that big, we should be able to see the radio waves, like, you know, the radio stations, they are transmitting radio waves. So we should be able to see that. We can't see it. So visible light is not an option. The correct answer is radio wave. So you need to look at that picture where I had a building, human, pin, and atom, right? So look at that picture. So wavelength, like larger than the radius of Earth, that is a wavelength which is a wavelength that is bigger than a building. So it is possible. We do have that large waves. So those who answers D, yeah, there are waves that larger than that wavelength, even larger than the radius of Earth. So it is possible. And those are under the category of radio waves. So anything larger than that size of a building, that's a radio wave. Okay. So, you know, like we detect these, the black holes. So in 2009 or 10, I remember like we detect the gravity waves. So gravity waves means, let me close this. So in 2010, I think 2016, as I remember, so people found out gravity waves. So Newton proposes about the gravity waves, but no one detected those. But those are radio waves, like when the two black holes are joining each other, so they will be moving around each other and combine at the end, right? So when they do that, like black holes are moving, they are making waves in the space. And those waves are navigating or propagating in the space, and we are receiving it, but they're really, really tiny energy, so we cannot detect it using our devices. But when the two black holes are combining each other, that's make a ripples in the space. So it's make a large energy emission, so it will create large waves that can propagate miles and miles. So we were able to detect one combination of two black holes in 2016, as I remember. It was a win-win, but that research group didn't win the Nobel Prize that year for physics, because the theory was found by Newton and they just prove it experimentally. But it was a great deal. Like in Arizona, I guess, they have these large pipes that it can emit the waves. So it always emitting waves and keep the waves going on in horizontal and vertical directions. And then when a external waves comes in, that disturb the current wave, so we can detect that disturbance. Okay, so yes, so those large waves are possible. All right, so I will call this as the end of the class for today. I keep 15 minutes window open for your questions. If you have any, if you don't have any questions, you may leave, but come prepare for the exam. You don't need to come to the Zoom meeting. You just take it on Canvas. But
Thank you.
if you need help.
Thank you.
Bye.
Yeah.
Thank you.
Bye.
Thank you.
Bye.
Thank you.
Thank you.
Oh, Goffran, are you here? I can send the link again. It's
Yeah.
on the
I have a question.
okay, 1 second. Let me send the link to her. Yes, go ahead. Who's having Goffran? Okay, so see, I always mix up your voice with another student. Sorry, even last week it was happened. I'm sorry about that.
It's okay.
Yeah, go ahead.
I noticed that you showed a slide
Mhm.
about Maxwell equation.
Uh-huh.
Well, I didn't find that slide in the PowerPoint.
Okay, yeah, I agree. I will upload that now.
Also, there's another page.
Yeah, I added 2 pages.
Yeah.
So I will upload the updated version now, right after the class.
Okay. And also about the Top Hat questions,
Mhm.
I couldn't find it in Top Hat for the next exam.
Okay, so can you share your screen with me by any chance, the top hat?
Okay. Can you see it?
Hold on. Yeah, go to assign. Okay, so the very first one, like you see 20 items? No, all the way top.
Yeah.
So yeah, so
Oh.
go click on there. Yeah, here you go. So those are the
Okay, thank you so much.
yeah, sure. Yeah, that's hidden if you didn't play with around. So that's why I always ask, like, can you see it?
Okay, thank you so much.
That you have
Bye.
access.
So just to be clear, the test is only on magnetism, not the topic we're learning right now.
No, it's only on magnetism. How many questions? Yeah, about less than 30. About, let's say 30 questions. Do you have any other questions?
I actually do have a question,
Yeah, go
but
ahead.
based on physics lab real quick. So I was looking over my labs and I turned in every single one of them, but you haven't, I don't think you've graded them. Are you going to be grading them anytime soon or?
Yes, there's one has been graded, right? My grader has graded
Yes, one, the very first one, I believe.
only very first one. Okay, he's working, like I have a grader for that, so he's working on that because in the beginning he had an issue with logging in, so he's working on. Yes, we will grade it soon. Let me check your work.
Okay.
I always think like I will grade it by myself, but I never get a chance to do it. I have what's going on, so that's why I have a grader. But let me look at yours. Yeah, I should grade it soon because I have to submit the midterm grades.
Yeah, like I've turned mine in and I don't know if it was either like the way I sent it was, I don't know. I was just wanting to make sure.
If he didn't say anything in the first one, then you should be good. Which section are you in? Like, what time is your lab class?
Oh, mine is 4 through 5:50.
4 to 5:50. Oh, that's why. So you're in my late section, so that's why you didn't get the grade yet. I'm sorry.
Oh, you're fine.
Actually, we graded 2 labs.
Which one?
First one and the second one. Don't you
Oh.
see that? Okay, for the second one, you received 85. Let's see why it is. Oh, yeah.
Oh, it says please convert to PDF.
Yes, because we have trouble opening this pages. It's submitted like page. Let me show you what we see from here.
Do you want me to send it to you in PDF in order for me to get that grade, or just
see this one? Okay, hold on a second. So this is what we see. So we cannot download. Even though we download, we can't open it. So what you can do is, let me check. So if you go to the lab assignment, it should be still open. So yeah, here. So it is still open. So you go to the lab assignments like a regular, the way that you normally do. So go and resubmit it. So you can click on the title and attach the newer version. But please put a note. Right?
Okay, that's fine.
Put a comment, like say, this is my resubmission. So you go to browse my computer and attach the new file.
Okay, I should probably check on the other ones because I know the last one that we did, I did the PDF because yeah, I just realized that the PDF. So, but
are you using a MacBook?
I am.
Yeah, that's why it does that, because when you're saving it, it's save like a page, but you can always change that. Like, you know, when you're saving, it's asking like what is the version you want to save. Save as. So when you go save as, it's ask you what. Yeah, you have the same problem on the next one.
Okay, and I don't know about the fourth one. I think the fourth one, no, it's still same way. Yeah, all of them are used pages. Yeah, I'll just have to fix that and resubmit it.
Yeah, I have to go over each one and tell you what it is.
Okay, let me see the first one. Did I submit it as
First one. Yeah, you have the same issue on the last one.
the first one? I turned it in as a docs, probably because I had an issue with Excel.
No, we didn't use Excel on the first lab.
Or well, with the we did. I think we did. I just took a picture of the I printed out the paper and took a picture and put it in a document on my very first lab.
I don't know why he put 100 here. Maybe he missed. Yeah, you had the same issue. We can't open your file. Oh no, you have 3 attempts. So let's see. Did you email me at any time?
No, I didn't.
Yeah, you sent me the Word doc.
Yeah.
Yeah,
Because
that's why you got the grade, because we can see your work here. Yeah, so let me show you. So if you have something, so I'm just showing you an example, okay? So if you go to the share screen, and let's say I want to save this Word file, so you go to File, and then I think it does the same in the MacBook. So you go to File and it's not responding. Give me a second. Maybe I'm not in the correct position. Sorry, it's slapped. So you may try on yours. So open a Word document and go to File and then Save As. Then you have option to save what type of file you want to save.
okay. All right. Thank you so
Then you
much.
can pick the yeah, I'm sorry, I have trouble opening Word today because I have to restart the program. Anyway, so you may try that. Okay, so when you submit, let me know so I will check it for you.
Okay. Thank you so much.
Yeah, sure. Sky, Cat, Dretty, Asrael, do you have questions? Okay, if not, I will close the meeting.